If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. So continuing from where we left in the last tutorial, we are talking about hyperparameter tuning, and I've already given you two important tips. The first one being that it's important for us to know what our hyperparameters are, without knowing which, we may end up giving the kind of values which are not welcomed, which will end up exhausting a lot of time but would not lead to best results for you. Second point that we discussed was about knowing the right metric for your model. So if you're targeting your performance around recall, then you should mention that as a part of scoring while tuning your grids. If you don't do that, by default, your models get tuned on accuracy, and that's where you find a bit of contradiction, that you're trying to get the best recall, but you're getting the best accuracy. In this video, building further on that, we'll be talking about the third most important point, and that is about defining the grid is not to be seen as a one-time task. It's not that we just assign a grid randomly and we just leave it there. We often have to revisit our grid depending on the outcomes that we get. So I'll show it to you through the hands-on demonstration as well. What do I mean by that? Plus, we will be talking about the randomized search CV. Now, randomized search CV is a boon for such models where we have a complex hyperparameter space. And with these models, if you get a relatively bigger data set, it's next to impossible to find the optimal solution using grid search because it's going to consume a lot of your resources. It'll take forever to train. So I'll show you how randomized search work. We'll do a comparison between the default model, the grid search-based outcomes, and the randomized search outputs. By the end of this video, you'll have a thorough understanding of the common approaches to hyperparameter tuning, and you'll be more confident applying these to practice. With this, let's get started. Please understand this grid is not something that is static. What do I mean by that? Let's say we ran a grid with min sample leaf values as 10, 50, and 100, or min sample split values of 30, 150, and 300. Now, if the best result that you get says min sample split value is 30, the best value we found is 30. There's no need to be just very happy about it. Why? Because you gave only 3 choices, of which it had to pick one of these. But it kind of suggests that you could have expanded your grid further downwards. You could have taken further smaller values. So in real world, when we talk about getting the results which matter beyond the academics where you learn for the sake of clearing an exam, we do not leave our grids just like that. We spend good enough time tuning the grids. If you get the best value of min sample leaf as 100, it simply suggests that you could have taken a bigger value further. We don't want to have too much to handle at once, but we can gradually fine-tune our grids as well. We can try to then expand it to values beyond 100 and see what's the best combination that we get. So once this finishes, we'll get to know how long did the grid search take, and then we will be comparing this with the randomized search approach to see if that works faster. All right, so finally it has finished, and you can see this has taken 214 seconds. How much did the default model take? If you compare it, the default model took only 1.78 seconds. So obviously, grid is great because it has experimented with about 162 combinations, and we've also done a cross-validation here. So cross-validation means for every single combination, we have tried repeating this 5 times. Now let's see the output. So best hyperparameters that we have found are, let's say the max depth is 7. Now, once again, it goes back to the same idea. We gave 3, 5, 7 as the best values, and it chose 7. It just suggests that we should now try bigger values as well. Within the given space, it has found the best result. But if we give it better space, it may be able to find better results as well. Same goes for min sample leaves, 10. So min sample leaf value, the smallest value we had given was 10. Maybe we can further try to adjust this value. Maybe we can try to further reduce this value and see if we get anything better. Min sample split, again, it says 30 is the best value. We could have taken a somewhat smaller value as well. But do it gradually. Take some values and try to fine-tune as you progress through it. N estimators, it says 50. Now, here we could have further maximized it. We could have taken higher values. Good that we started here. Now imagine, let's say the optimal result in this case was 10. Then obviously taking this value up to 100 would have been useless and it would have just wasted your time. So always try to optimize your grid based on the results that you get. It's giving you a good hint. Now you can try to take other values and you can ignore values like 10 and 30, expand to the north of 50 now. Let's look at the performance of this model because the last model was somewhat overfitting. Now, if you see, this model seems pretty stable, consistent in train and test. If you see, all these numbers are pretty close. It's not that your train results are all 111 and test results are 93 or 94%. So this model is relatively more reliable and stable. And one of the reasons why you would get 111 here all the time is because the default hyperparameter values are minuscule when it comes to min sample leaf and min sample split. So it kind of expands the tree to the last leg and leaves your model somewhat overfit. Now let's try randomized search CV. So we'll use the same parameter grid, or we can even use distributions using the range of values using NumPy or SciPy library. But we'll use the same parameter grid that we defined above for the grid search CV. This is the parameter grid that I'm referring to, even for the randomized search CV. The model that we're calling is random forest classifier. We've given it a different name this time, and that's how we are calling it. We are passing the same parameter grid. Now we are saying randomized search to randomly pick 10 possible combinations. We're not going to explore all 162 combinations like the grid search. We are going to pick any 10 random combinations and see how we are doing. So randomized search, of course, you can imagine is going to be faster. We are doing a cross-validation, which is 5-fold. We are scoring on recall, and we further have to mention the random state here. Why? Because this is a randomized search. It may not once again pick the same 10 iterations. So we have to mention it here one more time. We could again use n jobs. Again, we are starting the time, fitting, then capturing the end time, and capturing the difference up to 4 decimal places. You can see this is going to be a lot faster compared to grid search CV. So it will be somewhere in between the default and grid search. You can see it took 11 seconds. The default model took 1.78 seconds. The grid search took 214 seconds. And randomized search took 11.5 seconds. Let's see what the results are. So you can see results, again, are relatively stable. It may not be as good as what you got from the grid because you did not explore a lot of space. You just randomly took 10 combinations. But if you see, the results at least are stable. Whatever you see as your train performance are the kind of results that you also see for the test here in this case. So this is a trade-off. Now, if you're dealing with a data set which is too large and has a very complex hyperparameter space, it is next to impossible to be able to use grid search. Your system would just freeze for a long duration. So you may try randomized search, especially for such models, and that was the idea to explain this process to you with 3 important tips. Just to summarize, the 3 important tips were: you need to know the hyperparameters before you start assigning the values. Number 2 was you need to choose a scoring metric. Keep the objective of the problem you're solving in mind. Otherwise, by default, it's always going to tune the model on the accuracy, which may not be a metric of interest for you. And the third is that this grid is not static. Grid is something that will find out the best result amongst the possibilities that you've given it. It doesn't mean it's the universal best solution. So you may have to further adjust the grid a little bit, depending on the best outcomes, and then try to evaluate your models accordingly. That's pretty much about the hyperparameter tuning. While we took the example of a random forest here, you can imagine this approach pretty much applies to any model which has hyperparameters. Hope this helps.